Now we move to the second half of the opening ceremony, in which we have the privilege of hearing the Wartenweiler Memorial Lecture, delivered by Sir Andrew Huxley. The Wartenweiler Lecture is a prestigious keynote lecture in the ISB and is named after Professor Dr. Jörg Wartenweiler from Switzerland, who was the first president of the ISB. To formally introduce Dr. Huxley, I now call upon Dr. Walter Herzog. Dr. Herzog is a professor in the faculties of kinesiology, medicine, and engineering at the University of Calgary and a distinguished leader in biomechanics. In the context of the current ISB Congress, Dr. Herzog has done an outstanding job as the Congress Scientific Coordinator and Program Chair. Walter.
The Wartenweiler Memorial Lecture is awarded by the organizing committee each time to an outstanding scientist whose work has made a significant impact in the area of biomechanics. Today's Wartenweiler Memorial Lecturer would hardly call himself a biomechanist, maybe more a biophysicist or a muscle physiologist. Nevertheless, his work in muscle mechanics and muscle physiology has had a more profound impact on us in biomechanics than anybody else's. Today's Wartenweiler Memorial Lecturer is Sir Andrew Huxley. Andrew Huxley started his training at Trinity College in Cambridge in 1935, where he studied physics, chemistry, and mathematics. However, the rules at Trinity College required also that he had to take a fourth scientific subject, and he chose physiology. In 1939, he joined Alan Hodgkin for his first exposure to research on the giant axon of the squid. It's the collaboration with Alan Hodgkin and that type of work that led to the award in 1963, the Nobel Prize for Physiology or Medicine for that particular work. However, in 1963, when the Nobel Prize was awarded, Andrew Huxley had already, some 12 years ago, started to shift his research interests from nerve to muscle, presumably, as he said, because there appeared to be no obvious way of pushing the analysis of nerve excitation to a significantly deeper level. Once started on muscle physiology in 1951, he made many significant contributions very rapidly. Already in 1954, he published his famous paper with Rolf Niedergürki in Nature that showed that the A-band width remained constant and therefore gave rise to what we now refer to as the sliding filament theory, and of course at the time was a very controversial statement because A-band shortening was thought to be the major contributor to contraction and force production. In 1957, he published a paper on the theory of contraction, a very comprehensive paper, not only describing the mechanics but also the energetics and the whole mathematical formulations of what we now refer to as the crossbreed theory. And he told me that he actually had thought out that work in 1955, but didn't see any particular need to press forward with it or publish it very rapidly. However, then was invited by an editor of a journal to actually submit that type of work, and did so, not really realizing at that time what tremendous impact that type of publication, that particular publication, would have on the rest of muscle physiology and muscle mechanics for the next half of the century. In 1960, he left Cambridge for the University College London, where he became the head of the physiology department. He continued his muscle research there, and in 1966 published another classical paper with Gordon, Huxley, and Julian on the force-length relationship of the sarcomere, and relating specific stages of sarcomere lengths to specific events that happened on the force length relationship, and that formed the cornerstone for what we now call the crossbreed theory, or what we call the crossbreed theory. In 1971, another tremendously and revolutionary idea was introduced by Andrew Huxley and Bob Simmons in a Nature paper showing different attachment states of the myosin crossbreed to the actin could explain some of the fast transient phenomena that had eluded explanation until that time. And of course, the multiple attachment theories still prevail today and are really hardly disputed. In 1984, he returned to Cambridge and has remained active there in muscle physiology to date. He's still publishing very much outstanding scientific research in Nature, Journal of Physiology London, Biophysical Journal, all these journals that many of us dream of in publishing in. A few days ago, Andrew Huxley and his wife Regenda joined us for the Canmore Symposium on Skeletal Muscle. And there were several things that became quite apparent at this symposium. One was that ideas proposed almost half a century ago were still hotly debated and formed much of the foundation of what we still discuss and use today. It also became quite apparent that he would ask questions and comments that always provided a completely new insight and shed new light on the topics that were discussed. New insight that can only come from diligent work in a specific area over many years. I'm standing here in front of you today as the chairperson of the International Society of Biomechanics Congress here in Calgary, and in that capacity I would like to welcome Andrew Huxley to his lecture. However, and probably much more importantly, I'm also standing here in front of you today as Walter Herzog, the person and scientist. And in this capacity, I would like to welcome a scientific colleague and friend for whom I have great admiration and deep respect. Please help me welcome Sir Andrew Huxley to give his Wartenweiler Memorial Lecture on muscle mechanics and muscle physiology over the past 50 years.
Thank you very much. Well, thank you very much indeed, Professor Herzog, for these, two kind words. And I'd also like to say what a great honor it is, and I feel it so, to be invited to give this Wartenweiler Memorial Lecture at this conference of the International Society for Biotechnology. Well, I shall be speaking about present views, about how crossbridges work, and prospects and unknowns. Now, most of you will be aware of what present views are, so I shall be presenting things in a rather historical manner, trying to put them in perspective of the way that things were regarded at the time that each aspect of present views came up. And I haven't got any of the elegant kind of slides that are customary nowadays, because all my slides are reproduced from the original papers that I shall be quoting, and nearly all of those were in the days of black and white illustrations. Now, research on muscle has gone very much in the way proposed by T.S. Kuhn in his book on scientific revolutions. That's to say that progress of science goes in two different ways. One is discoveries that, well, may be very important, but are within the current framework of ideas. And that kind of research is punctuated occasionally by revolutions in which either some new observation or some new theory makes current ideas obsolete. Well, at the beginning of this century, a theory was developed, the lactic acid theory of contraction, according to which the contraction was due to folding up of long protein chains running right along the muscle fiber, and these were supposed to be kept extended by mutual repulsion between negative charges on these proteins. And when the fiber was excited, a certain amount of lactic acid was liberated, and the hydrogen ions from this neutralized these negative charges, reduced the internal repulsions, and allowed these chains to fold up. Now, the first use of the word revolution in connection with muscle, can I have the first slide, please, was made by A.V. Hill, grand old man of muscle and nerve physiology, died just over 20 years ago at the age of 90, had a great influence on my life. And he wrote a review in, I think it was 1932 actually, about the revolution in muscle physiology. And that revolution was the demolition of this lactic acid theory by an experiment of Lundsgaard, a Danish physiologist. In 1930, he showed that a muscle poisoned with iodoacetic acid was still capable of giving a substantial number of perfectly normal contractions without producing any lactic acid at all. So the lactic acid theory was out. The part played by lactic acid was replaced by other reactions that were already known, the splitting of phosphoryl creatine, and later that was replaced in turn by the splitting of ATP, which we all still believe. Now, the second revolution, the establishment of what's known as the Fenn effect, really well established by a paper published by A.V. Hill in 1938. Now, in this paper, this shows, this shows the total rate of energy liberation by a muscle as a function of the speed at which it shortens. And this energy liberation, well, this is the amount by which it increases over the energy liberation rate when the muscle is held at fixed length. And part of this appears as mechanical work, and the rest of it appears as heat. Now, this, well, just the fact that this energy liberation rate goes up when the muscle shortens is contrary to what everybody believed at that time, that a definite amount of chemical change was started by activation of the muscle. And, well, this is a very important result. But it does imply that the mechanical events largely govern the chemical events. And I think most people think of muscle contraction the other way around. Chemical events cause mechanical change to occur. Of course, that's in a sense true. But this is also true, and I think it's an aspect that even now doesn't receive as much attention as it deserves. And then the third revolution in this century was the establishment that length changes occur not by folding of great long protein filaments, but by sliding of two sets of filaments past each other. The next slide, please. This is a diagram from a paper of Hugh Huxley in 1953. It's just coincidence that the idea of sliding filaments was originated simultaneously in early 1953 by two groups, one Hugh Huxley together with Gene Hansen, who died rather young a few years later, and by myself together with Rolf Niedergerke. And it was a double coincidence, first that we got onto it by quite different approaches at just the same time, early 1953, and it's a coincidence that we have the same surname. We're not detectably related. And another discovery made in 53, both by Hugh Huxley together with Gene Hansen and by Wilhelm Hasselbach in the laboratory of H.H. Weber, was that the material that gives the high refractive index and the extra material here in each A band is in fact myosin, and that you can dissolve out the myosin with solutions that are known to dissolve myosin, and then you're left behind with these thin filaments composed mostly of actin. And then the changes in the striation pattern that really gave rise to the to the sliding filament theory were published in the next year. Hugh Huxley and Gene Hansen made these observations on separated myofibrils under the phase contrast microscope, and Rolf Niedergerke and I did it on living isolated muscle fibers from the frog. This is just the edge of one of these fibers, using an interference microscope, which is needed to get a satisfactory image on these rather large fibers with rather narrow striations. And this is an image in which high refractive index, that's to say high concentration of protein, appears dark. That's known as a positive image, and the fiber is simply being stretched passively, and you see that the dark bands, high refractive index bands, these are the A bands, which are also birefringent, they stay at constant width. And as Professor Herzog said, this was a total surprise at the time because all the textbooks told exactly the reverse. And another observation that we made, I think this may not be very easy to see. This is again a positive image in a region near the edge of the fiber where it's being activated by applied current. Instead of getting this pattern, there are quite narrow, dense lines, and watching this contraction develop, or watching the film from which these frames are taken, these thin, dense lines are at the middle of the A bands. Well, that was a surprise because there was a fairly well-known phenomenon in which dense lines appeared, at the middle of the I bands. Well, that did happen at a higher degree of shortening, but these dense lines appearing on a considerable degree of shortening in the middle of the A band suggested to us that there was this second lot of filaments that collided in the middle and either buckled at the ends or overlapped, making these thin filaments. So this idea of sliding filaments came from quite different types of experiment at just the same time. Well, of course, that raises the question, what makes them slide? And there have been an enormous number of theories produced. In a review, I classified these into 8 different categories of theory, and I think if you really divide them all up, you could probably get something like 100 different theories. And I'm not going to go over all of them, but I shall go on to what has survived. And 2 important aspects of, I think, nearly all current theories were based on experiments that had been done long before the appearance of the sliding filament theory. First of all, some experiments by Robert Ramsey and Sybil Street in the United States in 1940. They were one of the many husband and wife teams who've made important contributions in muscle research. They were the first to obtain satisfactory isolated living muscle fibers from frogs, And shows the tension developed by one of these fibers, starting at different initial lengths. 100% is just the length that gave the maximum tension. And the striking feature here is that when the fiber was pulled out to greater lengths, going up to double its original length, the amount of tension that was produced when the fiber was stimulated titanically declines just linearly. Well, this did not have an explanation under the then current theory of continuous protein filaments, but on a sliding filament theory, the amount of overlap between the two sorts of filaments would decline in this way over some range out here. But this was complicated by some observations that I made together with Lee Peachy from Philadelphia on these same fibers dissected from a frog muscle. And this is, well, observations made with a microscope along at different positions along one of these fibers. And the ordinate here is the spacing of the striation pattern. And in the middle of the fiber, it's fairly uniform. We stretch the fiber a bit, and the striation spacing gets bigger, going out even to 4 micrometers. But at the ends of the fibers, the striations remain much narrower. And that, of course, confuses any experiment made stimulating a muscle when it's been stretched like this. Even if the middle part is so far stretched that there's no overlap between the two filaments, there'll still be overlap at the ends. The muscle will contract and the tension will go up, the middle part being stretched. And we found that is exactly what happens. We put markers at different places along one of these fibers and stimulated the fiber. And this shows, plotted against time, what happened. Markers near, we'd got this stretched so that the spacing in the middle part of the fiber was about 3.6 micrometers, where we would expect there would just be no overlap. No shortening occurs. The spacing between the markers remains constant, but at the ends, the markers get closer together. There is overlap there, and there's tremendous shortening. This is shortening down to half its initial length. And then when we released the fiber a little bit, so that there was overlap all the way, stimulated under constant load, tremendous shortening all the way along. Well, this, of course, complicated measurements of tension at different lengths, and what is needed is some device to hold constant the length of some uniform region in the middle of a fiber. Together with Al Gordon and Fred Julian, we put a couple of markers on the fiber at places like fiber between, and then an optical and electrical device to measure this distance, and a servo to control the length of the total length of the fiber, so that this bit remained constant. And when we did that, we got the tension varied as this continuous line here superposed on the results of Ramsey and Street, showing that out here they still got very considerable tension, although there was no overlap. Well, this is an artifact, and it has caused a good deal of confusion and controversy from other groups who did not take the trouble to use servo control of the length of a uniform part of the fiber. And the next overhead, please. Well, it just shows this, this line in relation to the lengths at which that's just the length where there's just no overlap. This total of 3.65 micrometers being the sum of the lengths of the thick filaments, about 1.6, and the thin filaments, and the, about 2.05. And at this point, all the cross bridges are overlapped by thin filament, and then there's a region where there's no extra overlap, and then collisions start happening and the tension falls. Now, could we have again that first overhead? Now, this relationship between the total rate of energy liberation as found by A.V. Hill in 38, he did correct it later on, but at this time he believed it was a bit of a rectangular hyperbola. And Dorothy Needham, the lady half of another of these husband and wife teams, pointed out the analogy between this and the Michaelis-Menten relationship between the rate of an enzymic reaction and the concentration of the substrate. And this suggested that, well, the active sites in muscle were operating in a cyclic manner in the same way that any enzyme works cyclically. It causes the chemical reaction, the products are liberated, another substrate molecule is bound and is then reacted on. And that was a very important suggestion. And that suggestion was made in 1950, still a few years before any idea of sliding filaments. Now, these ideas, yes, the proportionality between tension and overlap suggests that there are active sites distributed throughout the overlap region between the two filaments, and that each of these active sites somehow contributes a certain amount to the total tension on that filament. And these are sort of independent force generators. Now, both that aspect and the cyclic action of these units are things that simply would not fit at all into the idea of continuous filaments, but they're naturally the things that you would expect to happen with sliding filaments. Now, the next slide, please. I produced a theory which was mentioned by Professor Herzog based on these ideas, and I think it's about the most elementary theory that one can have. Two states, these little projections from the myosin filament, which may either be detached as shown here, or they may attach to a site on the thin filament and pull it along because there's an elastic element built in here. And the idea is that the rate constant for these bonds being formed has an appreciable value in the range where, when it attaches, it will contribute to the a positive element to tension and help to pull the filaments along. And the rate constant for detachment is very low, so long as the attached thing and the springs are in a state of giving positive tension. But when sliding brings this to a position where the springs are resisting further movement, the rate constant for detachment becomes very large. And well, the shape of these was chosen so as to obtain analytical solutions for what happens with a steady speed of shortening, and it gave very nice fit to the relationships found by A.V. Hill between speed of shortening and tension development, and between speed of shortening and rate of energy liberation. So for these rather overall properties of the muscle, it worked very nicely, but it in fact failed completely on events that happen on a faster time scale. And for this reason, I've long regarded this as an obsolete theory. It was a step toward more complex theories which incorporate these features but incorporate many other things. And I was, well, astonished and I must admit very gratified only yesterday at this symposium in Canmore, a few miles away, that this theory is still used extensively for modeling the overall behavior of muscles in the living animal, where, well, complications, geometrical complications of the fiber arrangement are involved, and the events are slow enough so that these other things in muscle don't matter, and this overall behavior gives an adequate description of the force-velocity relation and the energy relations. Well, next step, next slide, please. Now, this is from a paper of 1957 by Huxley, some of the most elegant electron micrographs ever published, a longitudinal section of muscle getting a layer which just contains a single layer of thick filaments of myosin and thin filaments of actin, and you can see these little cross bridges going from one to the other. And yes, he showed that these in regions, well, if it's extended, or if you take isolated filaments, these projections are projections from the thick filaments, so they are part of the myosin molecules, and it was natural to suppose that these are the independent force generators, and this has been universally accepted ever since. Next step was in 1965 when another electron microscope group, Reedy, Holmes, and Tregear, showed in a different type of muscle that these cross bridges are at a different angle in resting muscle when they're more or less perpendicular, but in the rigor state, which is thought to correspond to the end of the working stroke, they were oblique in the if the movement into that oblique position would pull the thin filaments in among the myosin filaments. And that idea was developed by Hugh Huxley in a paper of 1969. The head of the myosin molecule would attach to the thin filament, and the force was generated by a tendency to rotate about this attachment, so that this part, the subfragment 1 of myosin, would act as a crank, pulling the thick filament along relative to the thin filament, and the connection was through this subfragment 2, which would be acting as the connecting rod. I mean, this is a sort of steam engine description of what might be happening. But this was a very influential paper, and, well, my thinking has been largely guided by this ever since. Well, then, around, well, it started earlier than this, in 1960, experiments showing these more rapid events that are not described by this 1957 theory. Next overhead, please. Now, the first experiments of this type were made by Dick Podolsky at NIH at Bethesda near Washington. Now, these are from some of our own experiments. Podolsky's experiments these are transient responses when a sudden change either of the load on the muscle or of the length of the muscle is imposed. And after a sudden, well, here a small increase of load, the muscle has been shortening slowly, load is increased, and a new, well, in this case, more or less stopping of this slow shortening is approached through a slow oscillation. Tension dropped again, another oscillation that slowly leads into a steady speed of shortening. But if we do, most of my experiments have been in the other method. The muscle is either stretched or shortened. During this stretch, there's a rapid rise of tension. It then drops, and then it creeps up again and down. but it's not actually an oscillation. It's a limited number of phases, simultaneous with the stretch, and then this early recovery, and then this delayed response, a rise in response to a stretch, and then a final creep back to the original. And well, this just shows the fast part of the contraction. Next slide, please. Well, this illustrates the kind of experiment that we've done. An isolated fiber is stimulated tectonically, tension rises, then we shorten it suddenly, tension drops, rises again part of the way, too fast to be separated at this time scale, that's 1/10 of a second, and then there's a bit of hesitation, or it may actually, there may be a drop of tension after a release, and then it creeps back to the original level, or after a stretch, the reverse sequence as shown in that last overhead. And this just illustrates the earlier part of this on a fast time scale. This early tension recovery is a very significant aspect, and this shows that this early drop is synchronous with the imposed shortening. Now, when a series of shortening steps is imposed of different size, there's again two striking non-linearities. With a small release, tension comes back very nearly to the original level, but with larger releases it falls away progressively. And the other aspect is that the speed of this early recovery gets bigger and bigger, the bigger the release, and slower in stretches. And the next overhead, please. Now this is the same as the top bit that we showed earlier, but it's just to show what I mean by this T2. That's the level of tension that's reached at the end of this early recovery. And now the next slide shows this T2 expressed as a fraction of the tension before the release, releases to the left, stretches to the right. And you see that for up to a quite moderate, quite fair size of release, it recovers back to the original tension, and then it drops away. And this early recovery fails with about more than something like 13 or 14 nanometers in each half sarcomere, each overlap zone. And this shows the tension reached at the end of the stretch or release itself, very nearly linear, but showing the kind of curvature that most biological materials do. But this nonlinearity and the increase in the rate at which that early tension recovery occurs, the bigger the release, these two nonlinearities, well, I would say to anybody, I mean, some people look for linear things that you can investigate conveniently by Fourier techniques. I say, treasure your nonlinearities, they will show something interesting. And these were the features that suggested a theory that Bob Simmons and I proposed in 1971. Next overhead, please. According to which, well, this is in a sense based on Hugh Huxley's scheme, but the tilting occurs in a limited number of steps, and the connecting rod is drawn as being elastic. But the key features are simply that the shortening process occurs in steps, whether it's tilting of a head or it might be lengthening or shortening of this element. And it's an essential feature that there's an elastic element somewhere in this system, wherever it may be. And this is a convenient way of thinking about what's happening without necessarily meaning to imply that it's really like this. So that at any one moment, there's a fairly rapid equilibrium between two states like this. If you do a shortening step, bringing the thick filament to the right, thin filament to the left, the spring is released a bit. It makes it easier for the head to tilt from that position to this. Chemically, this is a stronger bond than that one, so that the movement from this position to that is favored by the energy relations, but the reverse movement is favored by the stretch in the spring. And the early recovery phase would be the re-establishment of this equilibrium, so that these are going back and forth on the sort of 1 millisecond time scale all the time, but the relative amounts of time that it spends in these two states is shifted according to the changes of length. Well, it may be that the head tilts as a whole, or it could be that it's attached rigidly and bending occurs within the head. Well, next slide, please. One of the this just shows that this the line is the observed T2 curve, fitted quite well by a more recent version of the Huxley-Simmons theory. Next slide shows this is true also of the rates. This is taking account of elasticity in the filaments as well as in the head itself. Now we're thinking in terms of a cycle. In which there are, well, this shows the equilibrium between two states. But I think in terms of an alternation between a chemical event, the terminal phosphate of ATP being released while the head is in the same position, and then in the same chemical state without any further change, it makes this change of position and perhaps another one. Then, without change of position, another chemical change, the ATP released, and then again another ATP comes on, that causes it to detach. There's a tendency to speak in terms of each chemical state having a particular mechanical state associated with it. I prefer to think of them as alternating, each one permitting the next in the sequence. Well, the next big step came from a determination of the atomic structure of myosin and of actin by X-ray diffraction from crystals of these molecules. Tremendous feat in relation to myosin, completed in 1993 by Raymond and collaborators. And this is one of their diagrams, a cycle going round cyclically. Yes, this region, what's known as the catalytic domain of the myosin head, attaches and remains rigidly attached, and there's a hinge. The structure suggested a hinge at this point, and after it's attached, it bends at the hinge, pulling on the myosin filament, and then when ATP is bound again, it's released. But this is, well, a strong suggestion that's been generally accepted, that the key event is this conformational change within the myosin head, causing this part, referred to as a lever arm, to pull through a connecting rod to the other filament. Well, this is what I think most people would say is the current general idea. Well, recently this flexure at that point has been confirmed by fluorescence resonance energy transfer. You attach a fluorescent molecule at one side of the hinge. It emits its fluorescent light, and you have an absorber at the other side of the hinge, which may absorb, and the energy of the fluorescent molecule may get destroyed, get lost that way, so the fluorescence is reduced, and if the molecules are brought closer together by bending at the hinge, the fluorescence is there reduced. And a change of this fluorescence has been observed, indicating bending at the hinge. Now, there are two phenomena that are not explained yet on this. I'm not going to spend much time on them. The next overhead, please, shows an observation by Paul Edman in Sweden that the force-velocity curve, as determined by A.V. Hill, was part of a rectangular hyperbola. But Edman found that in this region, which is rather difficult to investigate, of slow shortening near the maximum tension, the speed of shortening is much less than would be expected by Hill's formula. And the next slide, another phenomenon by Lombardi. Oh, the next overhead, sorry. Phenomenon found by Lombardi in Florence, performing these shortening steps, but doing them in two stages. And when the two stages of the step, this is the length change, are within a couple of milliseconds, the bit after the recovery is very similar to what it would have been if the whole step had been made in one. And but then when you allow a bigger time interval of 10 milliseconds or so between the two parts of this step, there's actually substantially more recovery, quite unexpected. Now, these two phenomena, they're still puzzling, but they're puzzling in a different way from many other things. That's to say, there are too many explanations already available. For this one, there are 3 different explanations already in print, and for the other one, there are 2 in print, and I have in mind a third. But they are still puzzles. Well, now, we've been told in other contexts this evening about great surprises that have happened, unpredictable things. And 10 years ago, I would have said that it was totally impossible to record the tension produced by a single myosin molecule pulling. But this has now become a routine procedure in many laboratories. First done, next slide, please, by Spudich and collaborators at Stanford. This is a diagram of their technique. 2 beads with stuck between them a bit of actin filament, and these beads are held in light traps. That's to say, it's a focus of a laser beam, a very high intensity focus, and when light is refracted coming through this beam, the momentum of the quantum may be transferred to the bead, and the net effect of this light being focused is that this traps the bead at this position, and then you move the focus a bit by deflecting the light, and you move the bead. And then there are myosin molecules stuck on another bead here. You move these light traps down until the myosin hits one of these, and you record the response. And the next slide shows the responses that they recorded. This was published in 1994, just 5 years ago. And first look at this with a very low concentration of ATP, so that there's a long delay between an attachment happening and the beads being deflected by the myosin attaching, and there's a relatively long period before ATP gets at it and causes it to dissociate. With higher concentrations of ATP, these peaks are very much shorter in duration. And forces produced are of the order of a few piconewtons, a very small amount, and the amount of the linear displacement a few nanometers. Well, this kind of technique is extremely powerful and is one of the very promising things for the future, but at present it has serious limitations. Time resolution is not nearly as good as one would like and not nearly as good as one gets with single fibers, and the results from different laboratories are very different. As regards force, results range between an average of about 2 piconewtons and averages of 10 piconewtons. As regards the amount of shortening produced by a single attachment, ranging between about 5 and 15 nanometers. Well, just this year, several new complications have come up. Next overhead, please. This is from a paper in Nature only a few months ago. A group in York, in England, doing this type of experiment, not with myosin from a muscle, but with one of the very slow myosins from other sources like brush border. And here are these attachments, but you see that there's an additional step at the middle of somewhere in the middle of the attachment. So the force is generated in 2 steps. Now, this has not yet been observed with skeletal muscle myosin. This is on a very much faster time scale, but perhaps it happens, but happens so fast. If it happens within a millisecond, it would not be detected by present techniques. So we'll hope somebody will do this kind of experiment with a slower muscle myosin. And yes, further X-ray structures have been found. Another one, it's long been known that X-ray diffraction from muscle shows very little from the actin helix, unless the muscle is in rigor, when myosins are attached to the actin helix along the helical structure. And it then shows up. But during contraction, there's almost no accentuation of these layer lines. But recent observations, indeed, just in the most recent issue of the Biophysical Journal by 2 Russians with collaborators in Britain and in Italy, Bershitsky and Tsaturyan, looking, next overhead please, with temperature jumps. Temperature is suddenly raised by several degrees at this point, as is a skinned muscle fiber already fully activated. The tension rises over a period of some tens of milliseconds, much slower than the response to a sudden release here. You see the quick early recovery. And they show that this is not due to additional myosin heads being attached. There's no change of stiffness, but they do find an increase in these actin layer lines in the diffraction pattern. So this must be cross bridges already attached, going from a state in which they are not aligned with the helix, they must be attached or they wouldn't develop force, to another state in which they develop a bit more force and are in line with the actin helix. And the next overhead shows what this is suggesting. This is still very hypothetical. We developed this idea in conversation between myself and these 2 Russians, that the rapid recovery of force after a release might be this change, the lever arm tilting against this hinge point within the myosin head without the catalytic domain altering its position, but going from a state here where it can rotate around the axis of the helix, the actin, so that it does not follow the helix, to a state here where it's tilted further so that it develops more tension, but it's attached here rigidly in 3 dimensions so that it does follow the actin. Well, I think there are many surprises in store for us. Now I'm running out of time, so I I'll skip on. Next slide. Next, sorry, the next overhead. Well, that's a dye that just begun to be used. An article in the last issue of Nature, but one a week and a half ago, a dye which can be attached at the two ends to SH groups introduced to a myosin molecule by site-directed mutation, so that the axis of the dye relative to the myosin molecule is known precisely, and this is a very powerful method, but the results are not yet published, so we don't know what's going to come. Next overhead, please. Now, this is from a review that I wrote in 1970. Well, I gave a lecture in 73, and it's a list of unknowns, even if, well, the general outlines known at that time were correct. And, well, which structure is the elastic element? What's the nature of this elasticity? Is it rubbery or normal? What structure does the stepwise change? Is the attachment to a single actin? It's now fairly clear that it does attach to two. What kinds of bonds? Well, there are certainly electrostatic and hydrophobic bonds, but their relative parts are not known. Still not known how ATP causes myosin to dissociate. And what's the significance of the fact that each myosin has two heads? Well, those were a list of unknowns in 1974, still more or less unknown, and there are a lot more unknowns that have turned up. What fraction of heads are active at any one time in an isometric contraction? Estimates vary between about 15% and 50%. Is the attachment probability uniform anywhere within the actin helix, or does it vary within the actin helix? There is some evidence that from specialized muscles that it does vary. What's the origin of the rise of tension that occurred with a delay after a stretch, after the initial fall, and then there was that delay? It's the basis of the oscillation of asynchronous insect flight muscles. What is the amount of force from a single head? As I mentioned, different laboratories get values between 2 and 10 piconewtons. Again, what's the size of the stroke? And at the end of this article, I said, and I repeat it now, quite apart from the fact that all these things are unknown, the whole history of theories of muscular contraction during the last half-century shows that even when a set of ideas seems to be well established, there's a large chance that it will be overthrown by some unexpected discovery. But there are good prospects. There certainly will be great improvements in existing techniques, notably the single molecule techniques, single fibers in which the surface membrane has been destroyed, make all sorts of experiments possible because you can change the chemical environment of the contractile material, but these fibers are rather irregular, they give rather poor tension, there's rather little early recovery. I'm sure there'll be great improvements in those respects, and great improvements in time-resolved X-ray work. And there are techniques that are just beginning to be used, these doubly attached probes that I've just mentioned, fluorescence from single molecules, a modified ATP that is fluorescent, and you can get it to do its, these tremendously ingenious experiments, notably by Yanagida and his group in Japan, and with the changes of fluorescence due to the ATP diffusing away, correlated with the tension steps, site-directed mutations within the actin, the myosin head or in the actin, only just beginning to produce significant results. And when the structures of actin and myosin were published, I thought a whole industry would develop almost immediately of doing theoretical calculations of the interactions between the two molecules. As far as I know, only one such paper has so far been published, and it's had really rather little attention, which has surprised me. And I'm sure there'll be techniques that we think of as little now as we thought of single molecule experiments 10 years ago. Well, I've filled my time, so I'll stop at that point, and thank you very much. And I must thank again the organizers of this meeting for giving me this opportunity to present, well, the way that muscles work, rather from the mechanical aspect. I've said very little about their chemistry, or about only in passing about structure, and largely based on single intact fibers. That's the kind of work that I've in fact been involved in myself. Well, thank you very, very much.